Welcome back to The Deep Dive, the show that takes a stack of dense, intimidating source material and translates it directly into, I can definitely impress people at a dinner party with this.
Today, we're embarking on one of the most intellectually demanding quests in modern physics.
Yeah.
We're trying to truly merge quantum theory with Einstein's gravity.
So we're aiming for a framework that respects the full general covariance of a dynamically curved universe.
Exactly.
In other words, we're moving beyond basing quantum field theory QFT on the comfortable symmetries of flat spacetime, right? That flat space we usually work in, that's Minkowski spacetime.
Yes, and its rules are governed by something called the Poincaré group.
And for those of us who haven't memorized our group theory tables, what are those rules, really? What does that mean?
That's the perfect place to start. The Poincaré group is simply the collection of all possible symmetries in flat space. So translations in space and time, rotations and boosts, just moving at a constant velocity.
And standard QFT is completely built on the idea that these symmetries are fixed, unchanging, global.
Fundamentally dependent on them.
And Einstein tells us that's just fundamentally wrong. Spacetime isn't a fixed background. It's a flexible, dynamic canvas, a Riemannian manifold that responds to matter and energy.
And the attempt to unify these views is what we call quantum field theory in curved spacetime, or QFTCS.
Right.
And the moment you introduce that dynamic curvature, the central mathematical object you have to deal with is the stress tensor, T mu.
In general relativity, the stress tensor is the source of gravity. It tells spacetime how to curve.
It's the right-hand side of Einstein's equations. So if we want QFTCS to be consistent, the quantum field must also generate a stress tensor that, acts as a source for the gravitational field.
But wait, if the stress tensor is the source of gravity, how can the quantum version be, well, fundamentally broken?
Because in QFT, the stress tensor is formally defined as a product of field operators. Think of it like squaring the field, phi squared. This operation, when you apply it to quantum vacuum fluctuations, is formally divergent. It just gives you infinity.
Famously, mathematically meaningless. In standard flat space QFT, we fix this with normal ordering.
Correct. Normal ordering is essentially defining a vacuum state, the state of lowest possible energy, and then just saying anything that is just virtual noise relative to the 0 point gets discarded.
You subtract the infinite vacuum energy.
You subtract it relative to that 1/6 state. But the moment you introduce curvature, especially time-dependent curvature like a collapsing star, you lose that global, universally defined 0 reference point. That subtraction procedure becomes completely ambiguous.
And that is the core challenge. So the mission of this deep dive is to see how modern physics, guided by sources like Bryce DeWitt's foundational work, attempts to calculate a physically meaningful stress tensor in this environment.
And we're going to do that by exploring several concrete physical phenomena where space-time geometry creates these startling, really non-intuitive quantum effects.
Where do we start?
We will start by examining vacuum energy effects using the Casimir force, then see how acceleration can spontaneously generate particles, and finally, we will dive into the stunning physics of rotating Kerr black holes.
And the inevitable explosive thermal radiation predicted by Stephen Hawking.
Which is where it gets really interesting.
Let's do it.
So let's start with the mathematical necessity of symmetry when you're trying to define the vacuum. In flat Minkowski space, the vacuum is a trivial, simple state. It's the representation of that Poincaré group we mentioned.
The state of lowest energy. And crucially, it stays absolutely stable. You can move it around, wait a bit, it's still the vacuum.
Exactly. But once we introduce the complex asymmetric metrics of general relativity, we immediately face this problem of vacuum ambiguity. Without those fixed geometrical symmetries, well, there could be a million different ways to define 0 energy.
So how do you salvage a meaningful definition out of that mess?
The key is to look for a specific geometrical compass, the killing vector, COMU, a meaningful, non-arbitrary definition of positive versus negative frequency.
Which you need to define particles and antiparticles.
Right. That whole structure requires the geometry to be stationary.
Stationary means that the metric, the thing that tells you distances, doesn't change with time, right?
Exactly. If the geometry is stationary, it possesses a global time-like killing vector field, COMU. This vector field embodies the system's symmetry under time translation.
And if that COMU exists, we can use it to define a universally conserved quantity, energy, the letter E.
Precisely. And that allows us to select a specific preferred set of basis functions, these U sub I, that correspond to positive energy states. Once we have positive energy defined, The vacuum state is non-arbitrarily defined as the state where all the annihilation operators just give you zero.
It becomes the absolute zero reference point for energy for all observers sharing that stationary metric.
Yes.
But the whole point of QFTCS is dealing with scenarios where the geometry is not stationary or where that simple definition breaks down. Our sources highlight three major ways this conventional procedure fails.
Failure point number one, generic spacetime. In the universe at large, particularly in the early universe or near, say, a rapidly changing gravitational source, there may be no killing vector at all. The metric is dynamic everywhere.
And if there's no killing vector, there's no preferred time coordinate. And if there's no preferred time coordinate,
There's no non-arbitrary definition of energy or positive frequency.
exactly.
In this case, the very language of QFT, the particle picture, is likely useless.
So you can't even talk about particles anymore.
Not in a fundamental way, except possibly in highly localized regions where conditions are quasi-adiabatic, meaning the metric changes slowly enough that you can temporarily pretend it's stationary.
Okay. Failure point number two.
Space-like killing vector. This is the case where we have a global killing vector, but it may not be everywhere time-like.
And we are going to encounter this fascinating twist later with the Kerr black hole, I believe.
We are. In the Kerr metric, the time translation vector partial over partial it actually becomes space-like within a region called the ergosphere.
So what does that mean physically?
It means that for stationary observers outside the ergosphere, energy is conserved, but inside what we call time translation is actually a spatial shift for them. It completely destroys the simple notion of conserved energy for distant observers who try to extend their definition of time into that region.
That's a fundamental breakdown of what time even means in that highly dynamic region.
It is. And failure point number three, limited stationary regions. Space-time might only be stationary in distinct, separated regions. So think of space before a star collapses, that's the in region, and space long after it has settled into a black hole, the out region.
Both of those regions are stationary, but the actual collapse phase in between is not.
And that is the perfect setup for the Bogoliubov transformation.
Okay, so if we have two different stationary regions, we have two different legitimate sets of basis functions, the U's for the in vacuum and the, let's call them mu bars for the out vacuum. How does the transformation connect them?
It mathematically relates the two sets of functions. But critically, it relates the annihilation operator in one basis to both the annihilation and the creation operators in the other basis. The relation is defined by two coefficients, alpha and beta.
Wait, if the annihilation operator in one frame is related to the creation and an operator in the new frame, that sounds like a problem.
It is the entire point. If those beta coefficients are non-zero, it means that the in-vacuum state, when you look at it through the lens of the out definition, is not a vacuum state anymore.
The old vacuum contains new particles relative to the new vacuum definition. So the geometry changing or an observer accelerating, it literally generates real physical particles.
Exactly. This is the mechanism that underpins effects like Hawking radiation and the Unruh effect. And if the geometry changes dramatically enough, the transformation will generate an infinite number of these new particles.
Wow.
In that scenario, the two mathematical spaces, the two Fock spaces, cannot be related by a unitary transformation. This is the mathematical signature of severe particle creation by curvature.
So if the definition of the vacuum is arbitrary or localized, then our flat space trick of normal ordering, subtracting the vacuum energy, completely fails us in QFTCS. This brings us back to the stress tensor dilemma.
Precisely. Since normal ordering depends on the choice of the vacuum, it's generally arbitrary. It's inequivalent in different regions. So we have to leave T nu unnormal ordered and find another way to make it physically meaningful.
And that way is regularization. But we can't just subtract arbitrary infinities. The subtraction procedure itself has to respect a critical physical law.
And that law is the divergence equation, the statement that the covariant derivative of T nu is zero. This is the mathematical statement that the quantum field must obey the fundamental classical conservation laws.
Conservation of energy and momentum.
Yes. The complexity of QFTCS lies in finding a covariant, generalized subtraction process that always yields a finite result while preserving this fundamental conservation law across any arbitrary curved geometry.
It seems like the entire theory hinges on defining that subtraction process correctly.
It does. And the only way to test if we've done it right is to see if the resulting T nu can predict real, observable effects. which takes us to our first concrete example.
All right, let's get concrete. We're moving from the esoteric math of basis functions and Bogoliubov coefficients to something we can actually measure right here on Earth, the Casimir effect.
That weak attractive force between two neutral, parallel conducting plates.
Now, this seems unrelated to gravity. It's just electromagnetism and conductors, but you're saying it's fundamentally a pure vacuum energy effect.
Our sources frame it as a crucial pre-curvature effect.
Let me make sure I follow the connection. In section 1, we said the problem is the geometry changes, creating new vacua. Here, we aren't changing the gravity field, but we are fundamentally changing the boundaries of the quantum field.
Exactly. We're taking Minkowski space-time flat space and cluttering it up with conducting plates. From an infinite, unconstrained space to a highly constrained slab. The conductors enforce specific boundary conditions on the vacuum fluctuations.
The plates restrict the allowed modes of vacuum fluctuations between them. They can't support wavelengths that don't fit, so to speak. And this imbalance drives the attractive force, resulting in a vacuum energy density that is negative.
This negative energy density is the physical driver of the force. The formal calculation of the vacuum stress tensor for the Casimir effect reveals 4 key properties that really challenge our classical intuition.
Okay, property 1, the irreducible core.
When you do the raw calculation, you get an infinite cutoff-dependent part. But this part is mathematically identical to the vacuum stress found in uncluttered Minkowski space.
So it's like a background hum that's always there, with or without the plates.
A universal, infinite background energy that is physically unobservable. General relativity only responds to changes in stress energy, so this irreducible core is just discarded. It leaves the finite remainder that creates the force we actually measure.
That reinforces the idea that quantum gravity is concerned with differences in vacuum energy, not some absolute magnitude. Okay, property 2. Negative energy. The finite Casimir energy density between the plates is undeniably negative. The source material emphasizes this violates classical energy theorems, particularly those used in black hole theory, where positive energy is typically assumed.
This is a profound hint about QFTCS. If quantum fields can source negative energy densities, it implies that classical concepts like, say, the stability of singularities might have to be completely reevaluated.
Property 3. Frame and position independence of that finite remainder.
The finite part of the stress tensor is independent under boosts parallel to the plates, which is what you'd expect. But the fact that the energy density is uniform and constant between the plates is truly counterintuitive.
You'd expect the energy density of the vacuum fluctuations to get really intense right up against the boundaries, right? To diverge there.
And the raw components of the electric and magnetic field expectations do show the position dependence. They do diverge near the conductors. But when these components are appropriately combined into the total stress tensor T mu,
they cancel out.
The position-dependent terms cancel out in the bulk region. This leaves a uniform, constant field that leaves no internal gravitational imprint, only the external tension that pulls the plates together.
That's fascinating. And property 4, thermodynamic consistency. This bizarre substance negative energy density, tension pulling the plates in, positive pressure pushing them out sideways, it still behaves like a gas that satisfies the fundamental thermodynamic law.
The dE equals TdS P dV law. This is the crucial physical check. If you pull the conductors apart slowly adiabatically, so ds is 0, you are doing work against that vacuum tension.
And the work you do.
Exactly. Accounts for the measured increase in the total vacuum energy. It behaves like a thermodynamically consistent fluid, even though it's composed of nothing but virtual particles.
Now let's talk about the field type, because this was a major early sticking point. The scalar field versus electromagnetism. If early physicists tried to calculate this using a simple massless scalar field, it didn't work.
That's right. The simple scalar field model, where the field must vanish on the boundaries, it yielded an additional problematic term that resulted in a divergent integral across the slab. Infinite negative total energy. It suggested that maybe only the electromagnetic field could produce a finite, measurable effect.
So what was the aha moment that rescued the scalar field as a useful model for QFTCS?
They realized they needed to use the conformally invariant scalar field.
Conformal invariance means the physics doesn't change if you uniformly rescale all lengths.
Right, and mathematically, this enforces the condition that the trace of the stress tensor must vanish. T mu equals 0.
Why does enforcing that traceless condition solve the problem?
That problematic divergent term that plagued the simple scalar field is precisely the term that is not traceless. By enforcing T mu equals 0, that troublesome term just vanishes. The resulting calculation for the conformally invariant scalar field perfectly mimics the finite result of the electromagnetic field.
So that success gives us immense confidence in using the scalar field model, which is mathematically far simpler, to explore these really complex curved space-time problems where the details of spin might be secondary.
Exactly. It's our workhorse model.
So the Casimir effect isn't just a quirky lab experiment, it's a necessary testing ground, showing us that when we define our quantum fields, we have to preserve these crucial properties like conservation laws and sometimes conformal invariance to get physically sensible results.
And it acts as a perfect physical bridge to true dynamic geometry. We saw that if you change the boundary slowly, adiabatically, the entropy is zero. But what if we accelerate those boundaries significantly?
If the Casimir conductors are accelerated appreciably, they start emitting real photons, not just affecting the virtual vacuum energy. This means the entropy of the system increases, and we see real particle production.
Driven entirely by the acceleration of the boundary conditions.
This phenomenon, often called the dynamical Casimir effect, gives us the conceptual tool to understand general relativity. I've heard it described as a shaken electron mirror analogy.
That's a good way to think about it.
Walk us through that mechanism. How does shaking a mirror or accelerating it translate into real particles?
The surface electrons in the conductor are continually reacting to the vacuum fluctuations of the electromagnetic field. They produce exactly the currents needed to enforce the boundary conditions. That is, the electric field must be zero inside a perfect conductor.
Okay.
But when the boundaries are accelerating, those enforcing currents become sources for external field emission.
So the acceleration forces the electrons to perform this complicated dance to maintain the boundary condition, and that dance shakes the vacuum hard enough to spit out real, observable energy.
Precisely. To analyze this mathematically, the sources simplify the problem drastically to a two-dimensional space-time, one space, one time.
Which conveniently makes the field theory automatically conformally invariant, so we can use that successful scalar field model again.
Right. We model this with a single conductor, a barrier, whose world line is given by some function, ziz consani. We start in the vacuum state, and then the barrier begins to move.
And because the geometry is now non-stationary, the boundary is moving, this causes a mixing of positive and negative frequencies.
And as we know from section 1, this mixing is the Bogoliubov transformation at work. It leads directly to non-zero beta coefficients, which signify particle production. The beta coefficients quantify the physical energy imparted by the moving boundary to the field.
Let's look at a critical, highly studied case, constant acceleration. We analyze this using something called Rindler coordinates. This is fundamental because it connects acceleration directly to gravity.
Yes. If a barrier or an observer maintains constant absolute acceleration forever, a stable equilibrium state for the field can exist. The observer sees themselves surrounded by thermal radiation. This is the Unruh effect.
Why does an equilibrium state exist in Rindler spacetime but not in a generally changing metric?
Because Rindler spacetime, which represents a uniformly accelerated observer's view of Minkowski space, possesses a global time-like killing vector field that's parallel to the observer's world line.
The killing vector again.
Since it has a killing vector, it is stationary from that observer's perspective, even though they are accelerating wildly in the original Minkowski frame.
This sounds an awful lot like a black hole, but in flat space.
It is the profound analogy. The constantly accelerating observer cannot see past their Rindler horizon. The physics is mathematically identical to a static black hole horizon. Waves in that accelerated region can't get back out into the main manifold, just as nothing escapes a black hole. The constant acceleration creates their own personal thermal bath.
So the geometry defined by acceleration mimics the geometry defined by gravity itself.
Crucially, the sources highlight the dramatic physical meaning of the Bogoliubov coefficients in a transient situation. Imagine if the acceleration suddenly stops. The non-vanishing beta coefficients directly yield the number of particles produced.
So the particles were kind of virtual while the acceleration was happening.
In a sense, yes. It's only when the geometry snaps back to a new, stationary state that the particles become fully real and observable to everyone.
That concept, that particles are created not by the acceleration itself, but by the change between stationary states, that's the perfect conceptual springboard for tackling black hole curvature.
Now we apply these QFT concepts to true dynamic curvature. We transition from Rindler's flat space analogy to the Kerr metric.
which describes a rotating black hole with mass m and angular momentum j-ma.
Since the Kerr metric is independent of time and the azimuthal angle phi, we still have two key killing vectors, one for time translation and one to rotation. But as we hinted, the time translation vector, partial over partial phi, causes trouble.
It absolutely does. So let's look at the geometry. Feature 1, the ergosphere. This is the region outside the event horizon, but inside what's called the static limit, where that time translation killing vector becomes space-like.
And the physical consequence of that is the intense lens-thirring frame-dragging effect. Inside the ergosphere, everything, even light, is forced to co-rotate with the black hole. You simply cannot stand still relative to an observer at infinity.
It gets its name because energy can be classically extracted there, right? The Penrose process.
Exactly. Then you have feature 2, the horizon, the point of no return. And feature 3, the angular velocity of the horizon, omega h. This factor represents the physical rotation speed of that one-way surface.
And the first astonishing quantum effect here, caused by this interplay of rotation and curvature, is superradiance.
Superradiance.
Explain superradiance to us. It sounds like something that violates energy conservation on the surface.
It's the phenomenon where a bosonic wave, say a scalar or electromagnetic wave, is incident upon the ergosphere, but when it's reflected back toward infinity, it emerges with greater amplitude than it had initially.
Wait, a wave gaining energy upon reflection? That sounds like we just built a perpetual motion machine in the ergosphere. Where is this extra energy coming from?
It's not a violation of energy conservation. It's energy conservation relative to different reference frames. The amplification happens, provided the wave's properties satisfy the superradiant condition.
So if that condition is met, the escaping wave has gained energy, which must mean the waves that fell into the hole had a net negative energy, as seen from far away.
Precisely. Because the time translation killing vector is space-like in the ergosphere, the local energy of the wave is positive. But when that energy is projected onto the time coordinate of a faraway stationary observer, it appears as a negative energy component. This negative energy particle falls into the hole, effectively reducing the black hole's rotational energy, while the positive energy particle escapes, amplified.
This is the quantum analog of the classical Penrose process.
Yes. And since superradiance implies that any returning wave can be amplified, there is no stable ground state for the quantum field around a rotating black hole. The Kerr vacuum is unstable,
leading to spontaneous emission and decay. The black hole spontaneously emits particle pairs.
And to calculate the energy and angular momentum flux generated by this spontaneous emission, the work by William Unruh relies on calculating the vacuum expectation values of the stress tensor components at asymptotic infinity. Those components tell us the outgoing flow of energy and angular momentum.
We're back to the stress tensor, which we know is divergent. What happens to the infinities here?
There is a truly remarkable mode-by-mode cancellation. All the divergent, non-physical terms cancel out for all the standard quantum modes. The only contribution that remains finite and non-zero is precisely the contribution from the superradiant modes.
The one satisfying that special condition.
Yes, that finite remainder is the net outward flux.
That is an incredible act of theoretical consistency. The physics we observe is what's left after the infinities just cancel themselves out.
And this process must also be consistent with the most important classical theorem of black holes, Stephen Hawking's area theorem, which states that the surface area of the black hole horizon can never decrease.
So if the black hole is constantly losing mass and angular momentum through this process, how can its area not decrease?
Because the spontaneous emission process respects the theorem in a highly constrained way. Only particles for which a specific quantity, p minus m omega h, is negative are emitted to infinity. This negative quantity ensures that the mass loss and the angular momentum loss occur at exactly the right ratio.
So that the black hole's irreducible mass, the mass left if you spun it down completely, and thus its area, still does not decrease.
The quantum field is dynamically constrained to obey the geometry's classical rules. It's a huge step toward unification.
It is. Now, about the timescale for this effect, the decay rate.
The half-life for the loss of angular momentum is calculated to be proportional to m cubed.
What does that mean in practical terms for, astronomical objects?
It means the effect is extremely sensitive to mass. If a black hole were to have had its angular momentum significantly affected by this superradiant decay since the beginning of the universe, its mass must be less than about 2 times 10 to the 17 grams.
That's roughly the mass of a large asteroid. So superradiance is only really relevant for tiny primordial black holes. For a stellar mass black hole, this process takes far, far longer than the age of the universe.
And we should note, the source points out that this m-cubed timescale is an upper bound. The calculation is done for a single scalar field, but real physics involves photons, neutrinos, gravitons.
All of which are produced even more copiously, speeding up the overall spin-down process by orders of magnitude.
Exactly.
Superradiance is for rotating holes, but our next topic is even more profound because it applies to all black holes, even non-rotating Schwarzschild ones. This is, of course, Stephen Hawking's discovery that black holes are not perfectly black.
This moves us into the truly foundational work that established QFTCS as a major field. Bryce DeWitt followed Hawking's astonishing work by dealing with a realistic black hole formed by gravitational collapse, meaning a scenario where there is no pre-existing past horizon.
The model starts with a static in region before collapse and ends with a static out region, which has settled into a Schwarzschild state, so angular momentum is zero.
The key is that the non-stationary time-varying metric during the collapse itself causes particle production via geometry. Just as acceleration generated particles in the Rindler case, the dynamic curvature here generates particles.
So we define early time basis functions appropriate for the initial static state and relate them to the late time functions using the Bogoliubov transformation exactly as we did in section 1.
Yes, and the comparison of these vacua reveals the key physics. The most remarkable result comes when calculating the vacuum expectation value of the stress tensor at large distances in the steady-state region outside the horizon.
And the result is staggering. The particle flux is Planckian.
It is thermal radiation. The black hole looks exactly like a black body emitting at a specific temperature, seen through a filter that depends on the angular momentum of the wave modes.
And this thermal radiation is characterized by Hawking's temperature, which is determined only by the black hole's mass. T is proportional to 1 over m.
This is a monumental finding. The temperatures are completely independent of the messy details of what collapsed, the specific matter involved, the strength of the field coupling, anything like that. The thermal nature is purely a consequence of the geometry and the inescapable ambiguity of defining a vacuum across the event horizon.
The horizon itself is radiating. This forced a revolution in the way we think about gravity and thermodynamics. If a black hole has a temperature, it must also have entropy. This leads us to consistency with thermodynamics.
Jacob Bekenstein was the first to suggest that black hole entropy should be proportional to its area, based on the analogy between Hawking's theorem area never decreases, and the second law of thermodynamics, entropy never decreases.
And Hawking's derived temperature fixed the proportionality constant,
giving us the Bekenstein-Hawking entropy, S equals K times A over 4.
The sheer scale of this entropy is difficult to grasp. Our sources state that a solar mass black hole has an entropy of 5 times 10 to the 60th erg per degree.
Compare that to the entropy of the sun itself, which is about 10 to the 42nd.
Wait, the black hole entropy dwarfs the entropy of its progenitor star by a factor of 10 to the 18.
That is correct. It highlights the staggering capacity of space-time geometry to store information. The information contained in all the matter that collapsed is somehow encoded on the surface area of the horizon.
This confirmed the generalized second law of thermodynamics. The total entropy matter plus black hole must be non-decreasing, which allows the black hole area to decrease, but only if enough entropy is generated elsewhere by the radiation.
Exactly.
Now we check for stability. If the black hole is immersed in a radiation bath at its own temperature, it must absorb radiation at the same rate it emits. But is this equilibrium stable?
No, it is fundamentally unstable. It's an inverse relationship. The more energy a black hole emits, the smaller its mass m becomes. And since T is proportional to 1 over m, the hotter it gets.
It's a runaway positive feedback process,
Which leads to the explosive decay law.
The luminosity formula says the rate of mass loss is proportional to 1 over m squared.
So the decay law is explosive, not exponential. The mass cubed decreases linearly with time. A small hole accelerates its evaporation dramatically as it shrinks.
What are the implications for the age of the universe?
To have survived from the time of the early universe until today, a black hole must exceed 10 to the 15th grams. Anything smaller, any primordial black holes below that critical mass would have already completely evaporated away in a final, massive burst of high-energy radiation.
And what about charged black holes? Does the charge affect the evaporation?
Charged holes also experience emission, a charge flux, due to their electrostatic field. However, for relatively small black holes, Hawking's thermal process dominates over the classical pair production, causing the hole to rapidly discharge itself. It's like a thermionic current where the temperature drives the release of charged particles.
Finally, we arrive at the most provocative implication, one that loops back to our foundational issues in QFTCS, the naked singularity.
If the black hole's mass decays to zero in finite time, its event horizon must vanish entirely. The singularity, the point of infinite density where general relativity breaks down, would become exposed to the outside universe.
So, physics' greatest safety net, the cosmic censorship principle, the idea that singularities are always hidden inside event horizons, keeping the universe predictable.
Is violated by the consequences of quantum field theory.
Wow.
That is the implication. The explosive decay results in a vanishing event horizon, forcing us to fundamentally re-examine what happens to space-time itself when the background geometry evaporates completely. It raises profound questions about predictability and information loss.
We've established that the geometry causes these real physical effects, like evaporation and superradiance. But underpinning all this physics is the intense mathematical challenge of defining that consistent, conserved, renormalized stress tensor, T mu nu.
That is the ultimate mathematical and physical goal. We need a well-defined operator that describes both the dispersive virtual particle effects, like vacuum polarization, and the reactive real particle effects, like Hawking radiation.
And we know the expectation value of T mu nu is divergent. Our sources show a crucial connection between these divergences and something called the vacuum-to-vacuum amplitude, W.
Yes. The divergences in the stress tensor are contained entirely within the functional derivative of this amplitude, W, with respect to the metric. So, if you can calculate W, you can isolate all the infinities.
How do you calculate W in this complex environment?
Physicists turn to Schwinger's background field method. It uses a semi-classical approximation, often called the single closed-loop approximation, to calculate the effective Lagrangian, which encapsulates the full energy density of the quantum field.
When calculating this effective Lagrangian, the integral diverges at the lower limit, corresponding to the infinite energy cutoff, the ultraviolet divergence.
And Schwinger's genius was isolating these divergences by expanding the Lagrangian around the integration parameter, revealing three distinct divergent terms, each with a profound physical meaning.
Three types of divergences inherent in this curved spacetime calculation. Divergence 1.
A simple constant term. To absorb this infinite energy density, we must renormalize the cosmological constant in Einstein's field equations. This is the oldest divergence problem in QFT, now just generalized to curved space.
Divergence 2.
A term proportional to the scalar curvature, R. This term requires the renormalization of the gravitational constant itself, G. The vacuum energy is modifying the strength of gravity.
And divergence 3. A complex term quadratic in curvature derivatives.
This is the critical new divergence. It involves combinations of the Riemann and Ricci tensors. These terms arise purely from the non-commutative nature of differentiation in curved space. This is a profound consequence. The vacuum fluctuations force us to introduce new terms into the gravitational action that are quadratic in curvature.
So QFTCS doesn't just calculate quantum effects in curved space. It retroactively suggests that the gravitational theory itself must be more complex than the original Einstein-Hilbert action.
Absolutely. The coefficients of these quadratic curvature terms must be determined if we want a fully consistent semi-classical theory of gravity.
What about the alternative approaches like the Zeldovich-Starobinski scheme or adiabatic regularization? Those methods seem specific to certain geometries.
The source confirms a critical mathematical equivalence. Those frame-dependent methods are mathematically equivalent to Schwinger's generalized covariant method, provided the singularities are isolated first.
That equivalence is crucial. It means the specific physical results we found using those early techniques, like the thermal spectrum of Hawking radiation, are robust and confirmed by the more mathematically rigorous coordinate invariant methods.
But this success leads directly into a conceptual tension regarding conformal invariance. We saw earlier that the conformally invariant scalar field fixed the Casimir divergence because its stress tensor trace vanished.
Right, T mu mu equals 0. So if the underlying theory is massless and conformally invariant, W must be conformally invariant, and its derivative, T mu nu, should be traceless.
In that case, the divergence in W must be proportional to the square of the Weyl tensor, which is the only local geometrical term that is conformally invariant.
But wait, Schwinger's method yielded three divergent terms, including the cosmological constant term, which is not conformally invariant.
And this is the fundamental tension that QFTCS forces us to confront. To maintain perfect conformal invariance, you must discard that cosmological term. This highlights that regularization is a balancing act. You have to prioritize which fundamental invariances are preserved.
That sounds like a choice that has to be made based on experiment, not just pure theory.
It does. And the challenges don't stop there. When we consider truly massless fields again, we encounter the infrared problem.
And infrared divergence. That's a problem with large distances, not small ones.
Exactly. It arises at the upper limit of integration in Schwinger's formula. To regulate it, we must introduce an arbitrary cutoff parameter.
And what is the consequence of this arbitrary parameter?
It leads to an arbitrary shift between the renormalized classical action and the regularized quantum action. The consequence is profound. We confirm that the classical gravitational action must include terms quadratic in curvature, but because of the arbitrary cutoff, the exact coefficients of these terms cannot be purely derived from quantum field theory.
So, QFTCS predicts that Einstein's equations need additional high-order gravity terms. But the value of the constants governing those terms must ultimately be determined by looking at the real universe.
It's the ultimate self-referential problem. The quantum fields define the structure of the gravity theory, but the ambiguity inherent in the quantum vacuum requires empirical input to complete the picture.
So, what does this all mean? We started with the intense mathematical difficulty of defining a vacuum in a generally covariant theory, which required things like Bogoliubov transformations and a generalized covariant subtraction process for the stress tensor.
And we saw that this interaction of quantum fields with geometry leads to real, measurable physical effects, from the subtle negative energy density that drives the Casimir vacuum tension to the spontaneous energy extraction from a rotating Kerr black hole and culminating in the thermal explosive decay of a Schwarzschild black hole via Hawking radiation.
These physical effects are inextricably linked to the intense mathematical challenges of regularization. The ability to find a covariant subtraction process, like Schwinger's, is essential to yield the physically significant, regularized stress tensor T-reg that acts as the source for the gravitational field.
Without T-reg, you can't calculate anything real.
This whole QFTCS framework, particularly Hawking's discovery, forces us to accept that small black holes, under 10 to the 15th grams, cannot survive the age of the universe. Their explosive decay, driven by geometry, results in their complete disappearance within a finite time.
And here is the final provocative thought, one that forces us to question the stability of the cosmos. If a black hole completely evaporates, the event horizon vanishes.
This exposes the singularity, the ultimate point of breakdown, to the outside universe. The quantum world, therefore, appears to violate the cosmic censorship principle, forcing us to fundamentally re-examine what happens to the global structure of spacetime when the background geometry itself evaporates.
The physics implies that the universe, at its most fundamental gravitational level, might be unpredictable if QFTCS is correct. A spectacular and terrifying challenge indeed.
It is a phenomenal deep dive into the boundary between gravity and quantum mechanics. Thank you for guiding us through this material, and thank you, the listener, for joining us on the deep dive. We hope you feel slightly smarter about the complex geometries and the explosive fate of the cosmos now. We'll see you next time.